Example 3 is on using marginal analysis. It says the profit in dollars derived from selling X units of an alarm clock is modeled by P equals 0.0002 x cubed plus 10x. Use the differential dP to approximate the change in profit when the production level changes from 50 to 51 units. Again, notice the small change in units. The smaller change in units, just being 1 unit here, the more accurate or estimated the marginal is dP to the actual. And it says compare this with the actual gain in profit obtained by increasing the production level from 50 to 51 units. So we have two things we need to do. We need to calculate our estimated profit using marginal dP, and we need to determine our actual change in profit, which is delta P. Okay. So how do we find dP, the estimated change in profit? Well, the first thing we need to do is find the derivative. So let's find the derivative. If I find the derivative of 0.0002 x cubed, that would be 0.0006 x squared, plus the derivative of 10x is 10. And now I need to evaluate this at the original point. The original point was 50. So let me plug in a 50 there. P prime of 50 would be 0.0006 times 50 squared plus 10. Go ahead and put that in your calculator. I'm getting P prime of 50 to be 11.5. So that's the slope of the line, but that's not the actual marginal. That's not the approximation. Remember, we have to multiply that times the change in x. But that's not bad because remember, our change in x is from 50 to 51. Our change in x is simply 1. So our dx and our delta x is simply 1 because it's 50 to 51 units. So to find dP, the marginal of the profit, the estimated change, I do P prime of 50 times the change in x. And again, P prime of 50 was 11.5, and the change in x was 1. So my estimated change in profit is an increase of $11.50. An increase of $11.50 because that is when you sell from 50 to 51. So that means I made a profit of $11.50 off of the 51st unit alone. Well, let's see what the real profit was. How do we find out what the real profit is? Well, to find the real profit, you're going to plug in the two numbers. So we're going to find P of 51 minus P of 50. Let's plug those into the original function now. So P of 51 would be 0.0002 times 51 cubed plus 10 times 51. I'm going to take that value and I'm going to subtract off when I plug in 50. So when I plug in 50, it would be 0.0002 times 50 cubed plus 10 times 50. Plug that into your calculator. Be careful with your parentheses on this one. Let's see what you get. I'm getting a total of 1153. So our estimated change using differentials was an increase in profit of $11.50. My actual change was an increase in profit of $11.53. Again, very, very accurate here because our change in x was so small. That's how marginals are used, and the idea is, yeah, we did actually have the 51st data unit here, but in the real world, you'd be at the 50th and you'd be wondering what's going to happen for the 51st, and you could use differentials to help estimate the future. Okay, so let's just find some differentials, just more exact differentials. How does this one work? And this is really going to help you when you move on to your second calculus course in the sequence. And it might help actually when we get into integration later on in this semester as well. But let me show you what it is. Essentially what we're doing is we're taking the derivative with respect to x of both sides. So the derivative with respect to x of both sides of these equations. Well, the derivative with respect to x is simply dy dx, and the derivative with respect to x of 4x cubed would be 12x squared. But the idea is, instead of solving for y prime here, they want us to solve just for dy. So literally, you're solving for dy in this case. All you're going to do is multiply both sides times dx, and you would have dy equals 12x squared dx. That is the differential of y. 12x squared dx. So it's very similar to y prime before that we've been doing the entire semester. The only difference is we have to tack on this dx to the right-hand side of the equation, multiplying both sides by that dx. So let's look at b here. It's 2x plus 1 all over 3. No way I'm using the quotient rule on this one. I'm going to go ahead and separate this and say this is 2/3 x plus 1/3. Divide both terms by 3 is essentially what I'm doing. So again, I'm going to take the derivative with respect to x of the left-hand side and the derivative with respect to x of the right-hand side, which is 2/3 x plus 1/3. When I do that, I'd have dy dx equals, and on the right-hand side, the derivative of 2/3 x plus 1/3 is quite simply 2/3. But now I need to multiply both sides of the equation by dx to get dy by itself, and I'd have the differential y, dy, would be equal to 2/3 dx. Okay. Again, the only difference between this dy and what we've been doing is just y prime, or the derivative of y the entire semester, is we're just tacking on that dx to the end. Let's look at part C here. If I take the derivative with respect to x of the left-hand side and the derivative with respect to x of the right-hand side, on the left I'd have dy dx. On the right hand I'd have 6x minus 2. So now I need to take this and I need to multiply both sides by dx. The only thing I have to be careful of is make sure that I use parentheses in this answer. So I'm going to have dy equals, well, I'll just write it in the answer blank, 6x minus 2 in parentheses times dx. Again, if I said find the derivative of this function, you would have told me it's 6x minus 2. The only difference between the derivative and the differential is we're adding the dx. Look at part D. I have y equals 1 over x squared. I'm going to look at that as x to the negative 2, so I can take the derivative easier. I take the derivative with respect to x on both sides. When I do that, I would have dy dx equals, and that would be negative 2x to the negative 3, which is the same thing as negative 2 over with the negative exponent. Move it to the bottom. That'd be x cubed. Now I'm going to multiply both sides by that dx to isolate dy. And when I do that, exactly what I would have had, which was negative 2 over x cubed, but then I need to multiply it times that dx. So the differential y is equal to negative 2 over x cubed times dx.